My clock says that it's noon, so I think we'll get started on the second half here. I'm not sure how much of it I'll get through. I probably have a few more slides than I will get to, but I figure better that than the other way around. Before the break, I had just introduced the notion of hazard pointers, which are this general purpose technique introduced by Megad Michail in his paper that updated Tim Harris's work on singly linked lists, and became a general purpose technique that's available for lots of non-blocking data structures and is very widely used. The idea with hazard pointers is that I just want to make sure that no other thread deletes a node and reuses it while I still have a reference to it. So any node that I have a reference to that might be removed from the data structure by somebody else, I publish a pointer to in a global place. In many algorithms, a finite number of pointers per thread, often a small number, suffices. So in the linked list in particular, 2 hazard pointers per thread are all we need, the node that I'm at and the node that I just came from. If I have pointers to both of those in global locations, then anybody who deletes a node can look down the list of threads and look at the 2 published hazard pointers, or 0, 1, or 2 published hazard pointers for every thread, and if a node that's been taken out of the list is not referenced by any of those hazard pointers, then we know that no thread is looking at it, and no thread will be bothered if we reuse it for something else, so we can go ahead and safely reclaim it. But if there is a hazard pointer that points to it, then we need to put the node someplace until we can safely reclaim it. And that's commonly in the literature called a limbo list, a place where you put nodes that are in limbo until they can be safely reclaimed, because at the moment somebody has a hazard pointer that points to them. Looking a little bit more broadly, reclamation of space is easy if you have locks, because as long as you hold the lock, you can generally, in a well-designed algorithm, be sure that nobody is looking at anything in a conflicting way, so you can reclaim nodes that you take out of a data structure. Counted pointers and type-preserving allocation are a straightforward technique that works in many, though not all, data structures, but they need a double-wide CAS, which is available only on some architectures, not on others. Hazard pointers are a general solution, and they're portable. They are a little bit awkward in cases where you need an unbounded number of hazard pointers. Imagine that you're doing tree operations, for instance, and you need to publish a hazard pointer for every node on the path from the root to some leaf that you're searching for. In such a situation, you have to be able to kind of dynamically allocate hazard pointers, and that can be done, and there are libraries that do it, but it's kind of awkward. The more significant issue with hazard pointers is that every time you update a hazard pointer, you write down a pointer to something that you are using, before you can do anything else, you have to do a release fence. That is, you need to make sure that the write you just performed to the global location that announces your use of this node is visible to everybody before you perform any subsequent operation. And that fence is expensive on many architectures. So there's a non-trivial cost, maybe 30 cycles, as just a ballpark, associated with updating a hazard pointer on many architectures. And so people have been motivated to find ways to deal with memory management that would not involve an expensive fence every time you dereference a pointer. And there is a whole literature around memory management techniques in non-blocking data structures, which I certainly can't cover in detail today, but let me give you just a couple of pointers to ideas. Several people have used variations on what's generally called epoch-based reclamation. The earliest reference I know of to this is in Keir Fraser's PhD thesis at Cambridge University, but I'm not absolutely sure that he was the first person to use it. The basic idea is that you have a global clock that ticks slowly. And there are multiple ways that that global clock could be implemented. And whenever you are using nodes of a data structure, you write down what the epoch was in which you started performing operations. And when you want to delete a node, you wait until no thread is still active in the epoch during which you performed the deletion, or earlier. So basically, you wait until every active thread has moved beyond the epoch in which any outstanding references to the node might exist, and then you can safely reclaim it. The nice thing about this is that you only have to update this epoch advertisement once when you start your operation. So instead of doing a fence on every pointer dereference, you're doing a fence at the beginning of your operation only, and at the end of your operation. The problem, of course, is that because it's much more coarse-grained, the amount of memory that may be accumulated in limbo lists before it can be reclaimed is significantly larger, and in fact is unbounded if your threads can sleep arbitrarily long during preemption. Hazard eras are sort of a hybrid between the epoch-based system and hazard pointers. They update they associate an era with every pointer, and they update the global advertisement of what era you're in whenever you dereference a new pointer and it's in a new era. So as long as all the pointers you're following were created no more recently than the era you have already advertised, then you're okay. But as soon as you look at a pointer that comes from a newer era, you have to update. And that cuts down on the space some. Then just this last year, a student of mine, Hao-Sen Wen, and co-authors published an algorithm at PPOP that avoids the unbounded space allocation that can occur with indefinite preemption by allowing you to reclaim things that were created after a thread went to sleep. So a thread could go to sleep and it doesn't hold things up forever. New stuff can be reclaimed while the thread is asleep. And it could take a long time to go into details on that. I recommend the literature to anybody who wants to look at it. But in practice, most existing algorithms use counted pointers and type-preserving allocation, or hazard pointers, or possibly epoch-based reclamation. So let's move to a new data structure. Hash tables. There are, of course, multiple kinds of hash tables in the world. The most straightforward approach is to take the Harris and Mikhail lists and use them to represent chained buckets in a hash table with chained buckets. So we have an array of head pointers to lists, and then everything that's in the same bucket is in a singly linked list hanging off of one of those head pointers, and that's it. Whole algorithm, right? So we already have the singly linked algorithm. We know how it works. We use it for every bucket, but that gives us a hash table of fixed size. If we discover halfway through executing our program that we need a bigger hash table, we don't have a mechanism for accommodating that. There is an alternative approach to hash tables that's internal, where everything is in a statically allocated bucket and there are no chains, and you rehash on collisions. That's due to Purcell and Harris. There's a non-blocking version of that. I'd like to tell you about what's perhaps my favorite non-blocking algorithm, because I think it's just so amazingly elegant and clever, and that is a resizable chained hash table due to Shalev and Shavit from 2006. And this manages not only to be non-blocking, but to have O of 1 expected time for all operations, including operations that resize the table. So I can double the size of the hash table as part of my insert operation and still do it in constant time. And the key is that the buckets are hints. Everything that's in the hash table is in one singly linked list. And the buckets are pointers within the list that tell you where to start searching the linked list. Not only that, but the linked list is kept sorted not on key value, but on hash value. And the hash value is very strangely represented. So we have a singly linked list. The buckets are just hints. The singly list is sorted by a strange bit manipulation of the hash value, and the bit manipulation matters. So here's an example. I'm not going to try to give you the code, but hopefully you can get an idea about how the algorithm works by looking at the example. This is much smaller than any real hash table you would ever make, but it allows it to fit on the slide. At the moment, we have 4 buckets. Later on, we may decide to have 8 buckets, then 16, then 32. Every time we resize, we will double the number of buckets. And that will add 1 to the number of bits that we use in the hash value. So we have hash values that are long, 64 bits or something, and we don't use most of the bits. We use just a few bits to index into the hash table. Every entry in the array of buckets is either null, like 2 there, 2 doesn't point anywhere, or it points to a dummy node in the list. So dummy nodes never go away. They are the target of hints in the array of buckets, and they are interspersed among the data nodes at appropriate points. So this is an initial hash table that has in it not the keys 5, 15, 16, and 17, but keys whose hash values are 5, 15, 16, and 17. And we don't need the keys in my example, so I actually haven't shown them. I'm just showing you the hash values. And if you look up, and oops, I don't think my pointer's bright enough to see. No, works over here, but not on the slide. If you look up at the diagonal bit patterns above the buckets, they show you the bit manipulation of the hash value. So the least significant bit is either a 0 for a dummy node or a 1 for a data node. The rest of the bits are the bit reversal of the hash number. So for the node with hash value 5, for instance, the bits above it in reverse order other than the 1 at the end are 0, 0, 1, 0, 1. And the 1, 0, 1, of course, is 5. So the hash values are encoded in those bits in reverse order with an extra bit at the end to indicate whether it's a dummy node or not. So let's insert a node, a new node. This is going to have the hash value 9. And I've shown that in light gray. It's got the low order bit of 1 to indicate that it's a data node. And then we're 0, 1, 0, 0, 1, which is 9 for the hash value. And that gets inserted in standard numerical order in between the nodes with hash values 17 and 5. And we didn't have to do anything else other than find the right place in the list. And we did that by taking the 2 low order bits of the hash value, that is the 0, 1, and using those to index into the buckets. So we used the 1 entry in the buckets to find the second dummy node, and we traversed the list from there to find the place to where we should insert the 9. Then, let's say we decide we need to double the number of buckets. We allocate 4 more buckets. They're going to have values 4 through 7. We'll start using 3 bits of the hash instead of just the 2 bits that we had before, but all we have done is allocate an additional array to hold some more buckets, and they are uninitialized. I told you this would happen in constant time. That's assuming that the allocator gives us an array full of null pointers. If we have to go through and make them all null pointers, then it's not really constant time. But that's all we did. We didn't initialize any of the pointers. They will be initialized lazily, and we didn't change the linked list. But as it turns out, when we lazily initialize those pointers, they will end up interleaved, actually, evenly interleaved among the pointers that we already had. In other words, the new nodes give us a refinement of the hints into the list. They give us more frequent hints interspersed among the hints that we already had. So now, if we want to insert a new node, let's say one with hash value 21, we'll discover, because we're now using 3-bit hashes, that the 3 low-order bits, the 1, 0, 1, or 5, are for a hash bucket that is uninitialized. And so we have to initialize it. Well, where's it going to go? It's interspersed between 2 of the previous buckets. So if we look at only 2 bits, the 0, 1, that tells us the older bucket that has to be below the place where the dummy node needs to go in the list. So we take 1 bit off of our 3-bit hash. We have 0, 1. We use that as a hint to go into the list. We start perusing from there, and before we get too terribly far along, we discover the place between the 9 and the 5 where the dummy node needs to go for bucket 5, and we put it in with a non-blocking list insert. So now 5 is properly initialized, and we can keep perusing from there, and we quickly find the place where the 21 belongs. Then if we go searching for a node, we may again discover that we need to use an uninitialized bucket. Here, if we go searching for 30, which of course is not in the list, and we want to discover that it's not in the list, we compute what the hash value is. We take the low 3 bits, the 110, that needs to use bucket number 6. Bucket number 6 was uninitialized, so we use just the 10 to find out the nearest hint for where the dummy node for 6 ought to be. That was 2, so we go in where the 2 is, we peruse forward, and we quickly find that the 6 needs to have a dummy node right after where the 2 had it, and we put it in. So we get expected constant time for all of our operations, and they're all non-blocking. And it all works because we're using this strange hash values and choosing how many bits of it to use and putting things into a singly linked list. I have always loved this algorithm. Yeah. Is 16 misplaced? I hope not. These pictures are actually in my book, so if it's wrong, I need to fix something. So 16, 10000, and well, if the places where 2 and 6 go have no elements in between, because once we are starting to use 8 buckets with 3 bits of hash, it turns out that bucket 2 is empty. The things that used to be in bucket 2 are now split between buckets 2 and 6, and they all ended up in bucket 6. The only one, the 16, ended up in bucket 6. Repeat the question.
So initially in upper picture, the bucket 2 has no any pointers to the linked list.
Right.
So is it true that just access to some elements that is not in hash table, but that should go through bucket 2 will initialize this
yes.
pointer? Okay.
Right. So if I'm looking for something that needs to be in bucket 2, but bucket 2 is not initialized yet, that lookup operation will initialize bucket 2. Yeah. So let's see. The 16 with 3-bit hash, those 3, is using the 3 low-order bits. That's the 000, so that's fine. And down here, well, this is the problem, of course, when I try to dive into the details while standing on the stage. I don't know about you, but I can't think when I'm standing up front and talking. I can do one or the other. I can talk or think. Why is 16 where it belongs? Let's see. Mm-hmm. Well, it's sorted by the bit reversal of the hash with 1 bit on the end. So that the numbers that are in diagonal up there are actually in sorted order. Yeah, they're sorted as binary numbers. You know? Yeah, you're right. That's true. So what is going on there? It is. Okay. My impression right here at the moment is that that's wrong. I'm going to go double check that after we get done today. And if it is indeed wrong, then I need to publish an erratum on the figure in the textbook. Thank you. Yeah.
Could you elaborate how would you resize and that array of buckets or array of arrays in both constant time and log-free manner? You perhaps will need an array of arrays, and that looks non-trivial.
Yeah. So the original paper by Shavit and Shalev glossed over that. So if I've resized the table 10 times, then I have two small tables and one that's twice as big as either of those, and another one that's twice as big as that, and another one that's twice as big as that. And I have to get into the right element of one of those in expected constant time. And they don't talk about how to do that. What you need is one more level of search structure here that tells you which of the arrays to use, because each array has been individually dynamically allocated. And they are of successively larger sizes, except the first two are the same size. And for that, you can use a statically allocated array, which doesn't have to be very big in order to cover the largest hash table you could ever imagine having. And you use the high order bit set instruction on your machine to figure out which element of that second level array to use to point you at the correct sequence of buckets and to tell you which bucket within that sequence to use. In the picture, it's just, this is the 0, 1, that's the 4, 1. But in practice, you have to find the second array in order to index the 4, 1, and the extra level does that, and still in expected constant time. One extra level is all you need. Does that help? I'm not even positive where the question came from anymore. Okay. So that was all I was planning to say about hash tables. I recommend the paper. It is an eminently readable paper, and I will indeed double check my picture after the end of the class today. Double-ended queues are worth talking about primarily because there's a really nice double-ended queue algorithm that was the motivating example for obstruction freedom. Wait freedom and lock freedom have been around a long time. They were defined in Herlihy and Wing's original paper, and there were lots and lots of algorithms published that did one or the other, and everybody sort of assumed that there were only two interesting varieties of non-blocking algorithms. And then a group at Sun Labs realized that there was another interesting definition of non-blocking that was weaker than lock-free, and they used the double-ended queue as a motivating example for that. So the paper that introduced the notion of obstruction freedom does it in the context of this algorithm that I'll describe to you in a minute. In sequential algorithms, there is at least one really lovely application of a double-ended queue for finding the convex hull of a set of points in the plane. It's one of these classic computational geometry algorithms that everybody learns in a data structures or algorithms class. I am not aware of any compelling need for a true double-ended queue in concurrent code. But it makes a lovely algorithm. There are compelling uses of almost double-ended queues. In particular, a non-blocking queue that supports insert and remove at one end by one thread and remove at the other end by an arbitrary thread is a very widely used data structure for work-stealing schedulers. And there are multiple implementations in the literature of that sort of restricted double-ended queue that does push and pop from one thread at one end and pop by arbitrary threads at the other end. And of course, you can use a general-purpose double-ended queue for that, but there are specialized algorithms that are better for that purpose, and I'm not planning to go through them today. I am going to go through the Herlihy, Luchenko, and Moyer obstruction-free deck, and I'll mention the fact that you can make it unbounded by linking together multiple instances of the original algorithm. I had an undergraduate student, Matt Grachin, who did that a few years ago and published it at ICPP. In passing, I will note that the obstruction-free deck came after a previous algorithm from Magid Mikhail. Magid's algorithm is kind of complicated. That's the picture for how it works. Notice that pushes go through 3 steps. It takes 3 CASs to do a push. It can be helped once the initial CAS has happened. It requires a double wide CAS with the head and tail pointers both in the same word, so you can't do concurrent, non-interfering operations at opposite ends of the deck. So in practice, this doesn't get used, but it is the first published correct non-blocking algorithm for unbounded double-ended queues. Now let's go to the elegant one, with apologies to Magid. The elegant Herlihy, Lukchenko, and Moyer double-ended queue is most easily explained by taking its circular structure and flattening it out. So this is a bounded circular queue. It does support indefinitely doing pushes at one end and pops at the other. So if you just want to use it as a queue, it will go round and around and around and chase its tail, and that works fine. Or you can do pushes and pops at both ends. But if you do enough pushes that the 2 ends bump into each other, then it says, sorry, it's full. Okay? I've just drawn it flat because it's easier to draw that way. You'll notice that we have a left and a right end pointer that point to, hopefully, the first unused elements beyond the respective ends of the queue. So we have data in the middle, A through Z there, and we have a bunch of bottom elements off to the left and a bunch of top elements off to the right that are currently unused. When we join the 2 ends together in the circular array, we need one more kind of empty node, and we only need one of them, and it goes between the last top and the last bottom, and I'm not drawing that in the picture. Crucially, left and right are just hints. They don't have to be updated atomically with respect to the push and pop on the end of the queue. So when you want to start an operation at the left end, you look at the left pointer and see what it points at. If it points at a bottom element, you look at the element immediately to the right, and if that has data in it, you're in the right place. If you look at the element to the right and it's a bottom, then you know left is too far left, and you have to search to the right until you find the first data element, and then you know where left should have been, and you can fix it if you want, or you can fix it later. Similarly, at the other end, you look at where it points and move left or right, depending on whether you see data or top, and whether the adjacent element is data or not. Once you've found the right place, an NQ or a DQ is a 2-CAS operation. Every element of the array is a counted element. It has a serial number and the actual data. So you need to have a double wide CAS. The first CAS operation you perform is on your neighboring element. So let's say I want to do an insert on the left. I want to change that rightmost bottom element into a new data element. First, I will change the counter in the adjacent data element. I do that so that I will interfere with anybody who's trying to delete that data element. And then I try to do a CAS to change the bottom into the data element that I'm inserting. Similarly, if I want to remove on the left, I will initially change the counter in the rightmost bottom element, and then I will remove the data element by changing it to bottom. So if I have 2 operations coming at each other simultaneously, one wants to move the data this way by doing a push. The other one wants to move that way by doing a pop. Each of them will start by modifying the adjacent element and then try to CAS their own element. And they will interfere with each other. And it's quite possible that they will each force the other to restart, in which case you have live lock. And this could go on indefinitely. That's why it's obstruction-free. So it's possible that 2 operations bump into each other and fail and start over again, bump into each other, fail, start over again. Fixing this is an out-of-band problem. And one of the really elegant, cool things about obstruction-free algorithms is that in order to get the forward progress, you don't have to modify the code of the algorithm itself. You can deal with forward progress independently by saying any thread that tries too many times just backs off for a little bit by some random amount. And then odds are very good that whoever they're bumping into will make progress and get out of their way. So you can, in the scheduler, fix the live lock problem without having to embed the solution into your code. That's the argument, anyway, for obstruction-free algorithms. And this one ends up being dramatically simpler than Magid Mikhail's queue, and doesn't require left and right to be in the same word, so that you can do operations on the two ends of the queue simultaneously without them interfering with each other in this particular case. And again, I'm not aware of anybody who needs this algorithm in practice, but it's a nice way to introduce the notion of obstruction freedom. There are other things in the world that are obstruction-free. The most compelling examples I know of are much harder to explain. They're software transactional memory systems. Yes?
I'm just curious, is this a common approach, like this sort of random or exponential backoff to kind of probabilistically guarantee a kind of a weaker weight-free condition?
Well, the date on this was 2003. So this is much more recent than the notion, the original introduction of non-blocking data structures. So obstruction freedom, it's about 15 years old now, but that's young compared to other non-blocking techniques. There are algorithms out there that are obstruction-free. So if you look at several of the object-based software transactional memory systems, they have this flavor. The DSTM of Herlihy, Luchenko, Scherer, and Moyer, I believe, from Sun Labs from about 2004 is an obstruction-free software transactional memory system for Java. And there are several successors to that from various groups, both for Java and for other languages, that give you software transactions in an obstruction-free manner. And they need something in the scheduler to deal with the possibility of live lock. That something might just be standard, ordinary operating perturbations in the scheduler. It is often the case that if you use an obstruction-free algorithm, just the not exactly random but routine noise in your system from interrupts going off and the hardware choosing to run the pipeline in various ways gives you enough jitter between threads that anytime they bump into each other, they eventually reason it out. That's less true in the STM systems because transactions are long running, and you have this possibility that one transaction starts working on and gets through, 4 or 5 objects, and this one gets through 4 or 5 objects, and they bump into each other, and they both kill each other off. And there's so many different ways that they could interfere with each other that in their next run, the odds are still pretty good that they bump into each other. So you need some sort of contention management technique for software transactional memory. Trees are, of course, ubiquitous in computer science. And non-blocking trees are quite valuable and complicated and varied. There's a significant number of different tree algorithms out there, and I don't have the details of all of them in my head. If you're really interested in non-blocking trees and you want to talk details, Trevor Brown is around here somewhere, and he knows the subject backwards and forwards. It was his thesis topic and an ongoing subject of research for him. The first non-blocking binary search tree, not a rebalancing one, one that has at least the possibility of becoming a long spindly branch, but correct non-blocking binary search tree was due to Faith Ellen and several co-authors back in 2010. It is an external tree where all the data is in the leaves. The internal nodes just have keys to direct your search toward appropriate leaves. It is a lock-free algorithm, not weight-free. It's been extended to K-array trees by Trevor and Helga. There is an internal lock-free binary search tree, the first that I'm aware of by Howley and Jones, that came a couple of years later. That has data in internal nodes, not just in the leaves, so on average it's one level shorter than the external leaf-only tree. There are faster external trees from Natarajan and Mittal. I may talk a little bit about that in a minute. That extends the work of Ellen et al. By more clever marking of potential collisions in the tree so that you get more concurrency among operations that are nearby each other but don't strictly interfere with each other. The first non-blocking balanced tree that I'm aware of is Natarajan et al. From 2013. That was actually weight-free and very complicated and kind of slow. They have a lock-free simplification of that was published later that year that's probably more practical in real code. And then there are lots and lots of other extensions and variants. There was a nice paper by Drashler-Cohen et al. At PPOP in 2018, for instance, that showed how to add weight-free traversals and lookup operations to essentially arbitrary tree algorithms. So any non-blocking or lock-based tree, you could add weight-free lookup operations to it by using their work. And this is still a very hot area of research. So just to give you a flavor of it, let me sketch how Ellen et al.'s original algorithm worked. It's simpler than any of the other ones that are listed on that slide. So imagine an insert operation. This is a figure drawn directly out of their paper. I literally copied the postscript. You've got a tree on the left side of the picture, and you want to insert this new node C. You're going to do it by adding both the new leaf C and a new internal node containing the key D that will direct you in the right way. And the original leaf D is still there in the right-hand picture. It's just been moved down to become the right child of the new node whose internal key is D. The algorithm for insert is 3 steps, 3 cases. The first flags the to-be grandparent of the newly inserted node, that is B, the top one in the picture, flags it as the locus of insertion, if you will, the place where collision resolution has to happen for conflicting operations. So we put a flag in B with a cas, and as part of that flagging operation, we write down everything else that we plan to do. So we have a little record that says, I am inserting C into this tree, and I think I'm going to be doing it by putting a new internal node as your right child that's going to have your old right child as its right child, and I'm going to have a new left child of that. So you write all that down in a little bundle, and you put it into node B to say what you're doing. And anybody else who comes along and finds that node can finish your operation for you. So if you get preempted after writing that note down, somebody else can help it along. It's not actually the linearization point yet, but it's the point at which helping can happen. And so for the insert, your operation becomes inevitable at the point where you've put the flag onto node B. Then the second step, you swap in the new subtree, which you've already created as part of your planning operation. That's the linearization point at which the operation appears to instantaneously happen, and the thing that you're inserting will be found by subsequent searches. And then finally, you take the flag out of B to say that you're done, and you don't any longer conflict with any operations that may come along and try to use node B. 3 steps. The delete is a 4-step process. Again, 4 atomic cas instructions required. Again, the first one flags node B as the locus of deletion, and that will, of course, conflict with an insert like we had on the previous slide. So if a delete comes along and discovers that B has already been flagged by an insert or a delete, it will have to help that other operation and get it out of the way first. That's why we have that info record. Assuming B is not already flagged, we put a flag in that describes what we're planning to do in this info record. Then the new second step that wasn't there for the insertion is to mark node D, the parent, the in-between one, as frozen, meaning that we are planning to remove it from the tree. Then the third step is to swap in the new subtree that we've created, just B in place of D. That third step is the linearization point, and finally we unflag. And there's one point in here at which we may have to back out, help, and retry. In the insert, there was never a retry point. So inserts don't have to retry. They can be helped. Deletes can be helped, but deletes sometimes have to retry because you might flag the grandparent, then look at the parent, node D here, and discover that there's a conflicting operation going on with D that conflicts with both D and B. And at that point, you might have to help it, back out, and start over again. Actually, unflag, so back out, then help, then start over again. And the details are complicated, and they aren't entirely in my head, but it's a very readable paper. Yes? Yes. Yep. Yep. Yep, but notice that once you have found, because it's an external tree, once you have found the place where you need to do your insert or delete, you can tell locally that you are still in the right place. So if I've gone, and in particular, notice that node D there is the lowest level of internal nodes, and C is a leaf. I'm trying to delete C, and I'm doing operations on the leaf C, its parent and its grandparent. So they're in the bottom 3 nodes of the path from the root. And once I'm at that locale, no operation anywhere else in the tree can change the fact that this is the right place to delete C. And that's important. So I do have this sort of initial search that gets me here, but once I'm here, I know I'm in the right place, and that doesn't change, as long as I'm able to successfully flag B and mark D. If I can't successfully flag B and mark D, then there's been a conflict in my own local place, and I have to deal with that conflict. Okay. Let me mention the Natarajana Mittal variant on this. This is, again, a binary search tree, non-rebalancing, external. So the internal nodes are still just keys, but this allows more concurrency. The big innovation in this algorithm is to allow fewer operations to conflict with each other, to be a little bit more refined in our detection of conflict. And that's done by flagging edges instead of nodes. So a node has 2 children, and we can separately tag the pointers to those children, and operations on the different children will not interfere with each other. So I could be doing an insert on the left child and a delete on the right child at the same time, and they won't conflict with each other. And in practice, this actually turns out to give you significantly better performance for some workloads. In this picture, which again is drawn directly from the Natarajana Mittal paper, leaf G down there is a place where I'm planning to do an insert or a remove. F is G's parent. And B, way back up the picture, most of the time will be the parent of F. So in the usual expected case, which this picture is not, in the usual expected case, C marked successor and F marked parent will be the same node. The case where they aren't the same node, which is shown in this picture, is when we have some deletions going on simultaneously that we want to allow to happen simultaneously. And in particular, in this picture, which represents an unlikely but possible situation, all the nodes on the path from C to F, non-inclusive, so in other words, nodes D and E, are in the process of being removed. and we want to allow their removal operations to continue to occur concurrently with whatever we're trying to do down at leaf G. There are unmarked edges in this tree, lots of them presumably, and then there are two kinds of marked edges. The flagged edges, which are drawn in the picture with double arrowheads, are edges whose tail nodes are in the process of being removed, but whose head nodes, the ones they point at, are not in the process of being removed. And the dotted line arrows are ones where both the tail node and the head node are in the process of being removed. In this particular case, I guess so, yeah. So we're probably trying to remove node G so that subtree gamma will become the right child of E. So I guess this is a deletion picture. And as this picture suggests, but in a way that's more complicated than I'm planning to try to explain here. As this picture suggests, we can have multiple delete operations going on in the middle of this path from C to F and still successfully do something to G down at the bottom. And that's really the only, well, it's the innovation of this algorithm, is that it has higher concurrency than the original Ellen et al. Algorithm. And as I mentioned, there are lots of other trees in the literature, including now, as of fairly recently, rebalancing non-blocking search trees. Moving on, there are several skip lists in the literature as well. The first version I'm aware of is also from Keir Fraser's thesis. Keir had an amazing amount of stuff in his thesis. It was really quite impressive. He's also the guy who's responsible for the Zen virtual machine, or a lot of the work in it. Amazing guy. And it's a skip list that's based on the Harrison-Mikhail singly linked non-blocking lists. A version of this was worked on by Doug Lee, who's the principal architect of the Java Util Concurrent libraries. And so an updated version of Fraser's skip list is in the Java Standard Library in Doug Lee's version. And then after that, there was another version, slightly different, produced by Herlihy, Lev, and Shavit. And in the next slide, I'm going to suggest how that works and give you kind of a sketch of that particular skip list. So we have a whole slew of related skip list implementations there, and then there's an independent one that's a rather different technique from Fromitjev and Rupert that also uses H&M lists but has hints as backward links in those lists. And the principal advantage of that is that when you run into a conflict, you can recover locally in their algorithm rather than starting your operation over from the beginning. So a recovery from a conflict becomes an O of 1 operation instead of an O of log n operation. The disadvantage, of course, is that the backlinks introduce extra complexity and ongoing overhead. So it's unclear which one is going to perform better in practice, but clearly the one for the first bullet is easier to explain. So here's a picture to sort of suggest how that first one works. Everybody hopefully is everybody familiar with skip lists? Who has not seen skip lists before as a sequential algorithm? A few people. Okay, I got to tell you what skip lists are. Skip lists are totally awesome. They are a probabilistically log time search structure. And as the picture suggests, you have a linked list, a sorted linked list, that has some additional sparse lists associated with it. So the bottom level of links through the picture is a singly linked list. And if you wanted to find something in this data structure, you could find it simply by traversing that linked list until you ran into the element that you were looking for, or you got to something that was bigger and so you knew that it wasn't in the list. But the higher level lists allow you to skip over early stuff much of the time. So to insert something into a sequential skip list, this is a data structure due to Bill Pugh at Maryland, by the way, from 20 years ago? I don't know exactly. To insert something into a skip list, you choose a number for how many lists it's going to be in. So if we have a k-level search tree, then I pick a number between 1 and k for the number of levels that I'm going to insert it into. I pick 1 with probability 1/2. I pick 2 with probability 1/4. I pick 3 with probability 1/8. Each successive layer up is half as likely to be chosen as the layer below. Once I've chosen a number of layers, I just go ahead and I do it, insert in the sorted list at each of those layers. And because of the probabilities, I get twice as many entries, roughly, in each of the successive lists going down the picture. And with high probability, if I search in the top list first and find the last node that is smaller than what I'm looking for and go down, search in the next list, find the last node that's smaller than what I'm looking for and go down, I will in log time find what I'm looking for. That's the idea of the data structure. We want to do it concurrently and in a non-blocking fashion. We can use the Harrison-Michael lists at each level. And the idea in the version that I'm describing here is that the bottom list is definitive, authoritative. That's the one that matters. The upper level lists are hints. And if you move down, you have to double check to make sure you're in the right place in the list you just moved down to. And you may discover that you're not, in which case you have to back up in your code effectively, remembering the node that you came from, and try again. So inserts in this algorithm do first a Harrison-Michael insert in the linked list in the bottom. And if you have chosen that the tower above your node will have height more than 1, then you need to continue and do an insert in the list above. And then if it's of height 3, then you'll do an insert in the list above that until you've exhausted all the number of levels that you originally chose you're going to insert in. And each one of those insertions is a non-blocking singly linked list insert. But this means that the collection of inserts is not done atomically. The bottom one is the linearization point. The others are updating hints that are useful to other concurrent operations and that allow them to have expected logarithmic time, but aren't guaranteed to work. The inserts work from the bottom up. The deletes actually work from the top down. So if you want to delete a node, you remove it from the topmost list first, removing hints. And after you've removed all of the hints, you do the real linearizing removal at the bottom level. And the data structure is still correct when you've removed the levels above a particular node, because if you always just happened to roll the dice in a very bad way and you never made any multiple levels and everything was only in the bottom level, it would still be correct. Lookup, by the way, is wait-free. That always finishes in a bounded number of steps, regardless of what's going on concurrently. So now I'm into the part of the talk where I'm kind of surveying things in the literature with not a whole lot of detail, but hopefully giving you pointers that are intriguing, and you can go look up papers for data structures that you're particularly interested in. In 2013 at PPOP, Alec Morrison and Yehuda Afek introduced the linked concurrent ring queue, which is, to the best of my knowledge, the fastest concurrent queue on the planet. It is about an order of magnitude faster than the M&S queue that I described before the break. An order of magnitude, 10 times as fast. It's really a remarkable algorithm. It is extraordinarily complex. Has lots of corner cases. The code in the PPOP, the pseudocode in the PPOP paper has 2 bugs in it. One of them is a typo, pretty clearly, and somebody who's reading carefully would probably figure that one out. The other one is a logic problem, and my student Joe Israelovich solved the problem, figured out what had to be changed in the algorithm to fix this subtle logic problem, and he was very proud of himself, and he sent mail to Alec Morrison reporting this problem and the fix, and Alec's response was, "Oh yeah, we found that, and we published a fix on our website last week," and their fix was better than ours. So if you want this algorithm, you want to go to Alec Morrison's website, not try to build it from the pseudocode in the paper, mainly because there's a huge amount of engineering work in getting the C++ right, just translating the pseudocode to start with. So you want to use the version that Alec created. The key to this being fast is it uses fetch and increment rather than compare and swap. So concurrent conflicting operations all work in hardware. But it's not trivial to make that happen in a queue. There are array-based queues, there have been for a long time, that use fetch and increment and fetch and decrement. Eric Freudenthal, working with Alan Gottlieb at NYU back in about 1982 or so, came up with concurrent array-based queues that were blocking, not non-blocking, but they were based on fetch and increment and fetch and decrement. They were very fast. These were designed for the NYU Ultracomputer. If any of you know your multiprocessor history, that was an important historical machine. So the idea of using fetch and increment to find a new slot in an array has been around for a long time. But if you try to use that for a queue, you have this problem of, suppose there's a bunch of producers that are n-queuing things, and they all find the slot in which to add something by doing a fetch and increment. So this is my slot. Next thread, this is its slot. Next thread, this is its slot. That's great. We have dequeuing threads, consumers who come along. They're doing fetch and increments to find the slot from which to remove things. Slot from which to remove something, slot from which to remove something. But suppose that the dequeuers get ahead of the n-queuers. We just have a period of time when the queue is logically empty because there hasn't been enough data produced to satisfy the consumers. Well, the consumers are blindly performing fetch and increment. This is my slot, this is my slot, this is my slot, moving on down the line, and the producers are just sitting still. They're not doing anything. So we can have an unbounded number of run-ahead attempts by consumers to take things out of the queue that can take the head of the queue just an arbitrary distance down the way. And that's because the fetch and increment instruction always works. So the advantage is that we don't have conflicts in simultaneous operations that have to serialize in software. The hardware is doing the serialization of the fetch and increments for us, and that's where the performance comes from. But it introduces this really terrible problem of consumers getting ahead of the producers. And that's the fundamental challenge that they had to address in designing this algorithm, is what do we do about the case where the consumers get ahead of the producers? And the key to it is to give the queue what they call tantrum semantics, where at a certain point, a thread can get to a place of the code where it says, I give up. I'm just not doing this anymore. This queue is toast. Make a new one. And that's allowed. So you can just sort of label a queue broken and go on to the next one. And a broken queue can be finished. I mean, it might have some data in it. Consumers can still get that data out, but nobody can put anything in it anymore. You want to put some more stuff in? Get a new queue. And you can do that for any reason you want. You can do it because you've tried to dequeue too many times and gotten way ahead of the n-queuers, and you've gotten up and the head is caught up with the tail, and you don't know how to fix it. So you can just move on to a new queue. Or you can have somebody who finds a slot in which to n-queue, reserves it with fetch and increment, and then goes to sleep and doesn't actually fill it in. And some dequeuer comes along and finds the slot from which they're supposed to dequeue, but there's nothing in it. So they need to try again, because it's a non-blocking algorithm. We can't make them wait for the n-queuer to get around to filling its slot. The dequeuer's got to be able to try the next slot instead. But if that happens too many times, then we may have a few little holes in the queue where n-queuers have reserved a slot but haven't put anything into it yet, and we don't know when they're going to wake up and put anything into it, and we just may get confused by those slots, in which case we say, to heck with it, make a new one. And they can do that as many times as they want, and they have a linked list of these queues. And of course, you need the linked list to be unbounded. To have an arbitrary number of producers get ahead of the consumers, you need to be able to link together an arbitrary number of buffers anyway. So they have literally an M&S queue with all the operations that we saw before break, whose elements are ring buffers that may have several thousand entries in them each and are manipulated with fetch and increment. And lots of corner cases in the code, but really amazing performance. And in a few minutes, I'm going to talk about something called dual data structures, which is a teaser for my talk at Hydra tomorrow. And there are dual versions of the LCR queue that my student Joe Israelovich came up with. And so I will hint at those. A couple of times in this talk, I have mentioned universal constructions. And I should come back to that topic and say a little bit more about it. The idea of a universal construction is a way to take correct sequential code and produce correct non-blocking concurrent code. And there's two reasons you might want to do that. One is just to know that it was possible. And the other is to get an algorithm that you might actually want to use. And those are two very different motivations. The original non-blocking construction comes from Morris Herlihy's work back in the 1990s, and that was for the first purpose. It was to make arguments about the relative power of hardware primitives like test and set or swap or compare and swap, and to know which of them is fundamentally more powerful than the others and can be used to simulate the others. And Morris was able to prove that compare and swap and load, link, store, conditional are universal primitives, in that any non-blocking data structure can be created using just single word CAS or just single word load, link, store, conditional. And that proof of universality is created by demonstrating a universal construction. But it's not, a universal construction that you'd want to use to actually put something in your library. It exists for the purpose of showing the formal power of a primitive. I had a conversation with Morris on the boat last night about whether you actually might want a universal construction for the other purpose, and that's a little unclear. Almost any case you can think of, if you came up with a non-blocking data structure that was manufactured automatically from a sequential data structure, there would be a way to make it faster by tuning it by hand. And if you're going to put it in a library and have lots of people use it, you probably want to make it faster by tuning it by hand. So probably the carefully handcrafted algorithm is what you want in any case that you really want to put into a library. But there are times when the universal construction may be useful for other purposes. And in particular, transactional memory systems can be thought of as universal constructions plus, if they're non-blocking. So as I mentioned, some transactional memory systems are non-blocking. And how many people have heard of transactional memory? Okay, how many people have not? Okay, just a couple. This is not a talk about transactional memory. But the idea in transactional memory is twofold. First of all, at the program level, you say what you want to be atomic, and you don't have to say how to make it atomic. So you can basically just bracket a section of code and say, the stuff inside here, that should be atomic. Dear system, make it so. Right? And then under the hood, the implementation uses speculation. It guesses that nothing conflicting is going to be going on at the same time, and it executes as if there were no conflicts, but it also watches to make sure that that was actually the case. And if it actually sees a conflict, it backs out and retries. So it's a speculative implementation, and what it's speculating is lack of conflict. And if there is a conflict, it's designed to be able to back out and retry. That's transactional memory. It can be implemented in hardware, can be implemented in software. Software versions can be lock-based or they can be non-blocking. Most of them are lock-based. A few of them are non-blocking. I'm aware of one that's lock-free. That's the obstruction STM, which is, again, Keir Fraser's thesis work. And I'm aware of several that are obstruction-free. Those can be thought of as non-blocking universal constructions. So I can take sequential code, use a non-blocking software transactional memory system to create something, and I might actually want to do that even though it will be slower than a hand-tuned algorithm because I get some extra stuff. That was the plus plus part. The plus plus part is atomic composability. So if I want to remove something from this set and put it into this set as a single atomic operation, software transactional memory will let me do that. Where there is never an observable situation in which it's in neither set or in both. And if I have a correct set in my library and I have another correct set in my library, I don't have a natural way of putting the operations together and making the entire composite operation atomic unless I have something else. And that's what STM might be good for. Final bullet here I made reference to before the break, and that is a construction developed by Erez Petranka and his students over a several-year period that showed how to take lock-free structures and turn them into weight-free structures using a construction they call, or an idiom they call, a fast path, slow path technique. The idea is most of the time you do what the lock-free structure is designed to do. So you have an optimized, handwritten, really cool, in your library, lock-free, non-blocking data structure. But you'd like to guarantee that no thread ever starves. And lock freedom doesn't give you that. You want weight freedom. So what you do is basically run the lock-free algorithm. And if it forces you to back up and retry, you back up and retry. And you do that a few times. And after a while, you get impatient. And you say, I might be starving, right? I don't want to starve. So I will write down in a globally visible place what I am trying to do. And every other thread knows that every once in a while, it has to look in that global place to see if there's anybody who thinks they might be starving. And if so, it has to help them. And that's basically the idea. It's much more complex than that. But the basic idea is most of the time you just do what the lock-free algorithm would do. But every once in a while, that doesn't work for you, in which case you advertise the fact that it isn't working for you, and everybody else is obligated once in a while to look and see if you're having trouble and help you. So most of the time you don't tell anybody what you're doing, and most of the time you don't try to help anybody, but if there's any danger that you're starving, you do tell somebody. And once in a while, you look for people who are starving so that they don't starve indefinitely. And that construction can deliver remarkably good performance in practice, but it does require that you have this global structure whose size is proportional to the number of threads. Tomorrow at Hydra, I'm going to give a talk on another topic that I don't want to duplicate here, but let me give you a little bit of an advertising blurb for it. You may have observed that implicitly throughout everything I've been talking about today, I've described remove or dequeue or pop operations that return null or bottom, if you will, in the case where the structure is empty or what you're looking for is not there. But think of all the algorithms where you want a concurrent queue. I mean, imagine your e-commerce pipeline, for instance, and you've got a thread that's responsible for taking requests off of the network, and it puts them into a queue. You know, it decodes them, puts them into a queue, and then you've got a pool of business logic threads that are pulling things out of that queue and doing stuff. And sometimes they need help from a database backend, so they take requests and they put them into a queue of requests for the database. And then there's a pool of threads that's responsible for taking things out of that queue and doing the database operations. And most of you have probably seen something that has this flavor to it. Well, that's the most common use of a queue, probably in all concurrent programming. And if you try to take something out of the queue and it's empty and you're a worker in the next stage of the pipeline, what are you supposed to do? You just looked for work. There wasn't any there. So you don't have anything to do until there's work. So eventually you have to look again, right? Maybe immediately, maybe you wait a little while, but you look again and maybe there's no work. And so maybe immediately or maybe after a little while, you look again. You sit in this loop that says, while there's nothing to do, keep looking. Well, what happens when you keep looking? You get in the way of the threads that are trying to put something into the queue. And you use processor resources that threads that are trying to put something into the queue would like to have. They'd like to run on your core. So really, you want to wait until there's something available. But that's blocking, right? I mean, we're talking about a non-blocking algorithm in which you want to block for stuff that you want to take out of a data structure that's empty, which seems like it doesn't make any sense, but it actually does. And that's what dual data structures are about. They're a way to introduce condition synchronization into non-blocking data structures without turning them into blocking data structures. And that's what my talk about is tomorrow. The key idea is that when you try to take something out of a data structure that doesn't have that in it, you insert a request instead. So if what you want is not there, like the queue is empty, you put a thing into the queue that says, I want something. And by the way, I'm asleep waiting on this semaphore over here. So I'm not bothering anybody. And when somebody comes along, a producer puts something into the queue, or is about to put something into the queue, they discover that your reservation is sitting there. And instead of actually putting the data into the queue, they take your reservation and satisfy it. And it's a little tricky to do that in a way that doesn't introduce blocking, but we can do so, and I'll talk about that tomorrow. If you haven't noticed, I'm now in the part of the talk where I'm talking about random topics. and I'm glad to take questions about any of this, or about any of the other stuff that came up previously. Yeah. Anybody?
I have a question inspired by the lecture of Leslie Lamport.
I didn't catch that, I'm sorry.
I have a question inspired by the lecture of Leslie Lamport.
Yeah.
Have you ever tried to use TLA plus to prove the correctness of the algorithm? I think it's...
I have not. Doing so has been on my to-do list for several years.
Okay.
About all I can tell you is that I feel very guilty about not having done it yet.
Okay, thank you.
Yeah. Whoever. I'll let Peter arbitrate.
So you were talking about trees, and apparently this is a hard task to design a lock-free tree. But what do you make of persistent data structures? Apparently, it occurs to me that you can take a persistent tree implementation and then just, do a cas with a counter. So it should be lock-free, right?
When you say persistent tree, do you mean persistent in the sense of the history of the data structure is preserved in the data structure?
Yes, yes.
The way it would be in a functional programming language
yes,
implementation. Yeah. Such data structures are very handy. They can be used for things like supporting wait-free lookups. So, aggregate operations. So suppose I want to perform an operation on the entire tree, like add up all of its elements, so I need to search the entire thing. If other operations are happening concurrently, inserting and removing things, logically every one of those conflicts with what I'm doing, and in a straightforward implementation, my operation would be forced to restart over and over and over, and I could starve. But if I have a persistent data structure in the sense that it's history preserving, then I figure out what version of the data structure I'm going to use at the very beginning, and I traverse that instance of it, that snapshot in time. And other operations that are going on concurrently are creating new instances in time of the data structure. And I end up linearizing near the beginning of my operation, but that's perfectly acceptable. It's a very slow, long delayed return of an operation that linearized shortly after the call. So that's a beautiful use of that sort of persistent data structure. There's another meaning of the word persistent that I'm going to have on a slide in a couple of minutes. That's persistent with respect to the values in memory after a power failure, right? And we now have byte addressable fast memory that preserves values across power failures. And we're likely to have other technologies of that kind coming along in the near future. And for those, it's interesting to talk about concurrent data structures that are correct with respect not only to executing threads, but also to recovery threads that come back after a power failure. And there's actually an interesting intersection between the two definitions of persistent, because the functionally inspired data structures that are persistent in the history-preserving sense are a useful tool for building consistent data structures that survive crashes. And we had a paper on a key-value store called DALI at DISC a couple of years ago that does exactly that. That uses the two different kinds of persistence in the same paper.
That's cool. So actually the question was like, there seems to be a cheap way to get in a lock-free tree by just taking a persistent data structure in the first steps. But like, why don't people do that? So can you compare it to the lock-free tree implementation that you mentioned?
It's not as easy as it might at first appear. So it addresses the challenge of a long-running operation continually getting forced to restart by concurrent updates. But it doesn't address the conflicts between updates. So if I'm trying to put a 3 into the tree and you're trying to put a 4 into the tree, and they need to end up having a common parent, it doesn't deal with the fact that somehow we have to end up with a data structure in the most recent version that has both of them in it.
Yeah, I mean, I can just do a CAS with a version in it, right?
Well, at some point there'll be a CAS that determines which one of us goes first. But maybe we're trying to rebalance the tree at the same time, and if we stuck them both in, the tree would be out of balance, so one of us has to do a rotation, and the rotation ends up modifying several nodes, and the paths end up in different places, and maybe at the end, my 3 is supposed to be here, and your 4 is a successor, but their closest common ancestor is 4 levels up in the tree after the rotation. I mean, all of that's got to get resolved somehow. So conflicts between updates aren't trivially resolved by having a persistent data structure.
Yeah, thanks.
Yeah.
Yeah. What do you think about non-linearizable data structures, and do we really need linearizability in common applications like servers?
Clearly, there is a use for things that don't linearize. I mean, if nothing else, look at all of the work on eventual consistency in distributed systems. Clearly, people are willing to have things that don't have a clear total order of updates over time. But that doesn't mean they're happy to have that in all cases. There are certainly algorithms, I mean, my bank, for instance, where I want to make sure that the updates all linearize. Is there room for interesting research on shared memory data structures that don't linearize? Absolutely. But I'm mostly interested in those if they have a motivating use case. They may be interesting just from an intellectual theoretical perspective, but if you want to work in that area, I would encourage you to look for an application that is happy with the relaxed semantics.
Mm-hmm. Yeah. Thank you.
I have a question about skip lists.
Mm-hmm.
When you insert element in skip list, how do you know the height of the tower above your element? In how many queues above you should insert your element?
Yeah, so in a skip list, you need a pseudo-random number generator with known statistical properties. So the height of the tower above a node is selected at insert time, and increasing heights have exponentially decreasing probabilities. So if you have a fair coin, you could do this by tossing it heads, you insert at level 1 only. Tails, you flip the coin again. If you get heads the second time, you insert at level 1 and 2. If you get tails the second time, you toss the coin again. So you want the exponentially decreasing probabilities, and that gives you the expectation that each list will have half as many elements as the list below it. Yeah. And that goes back to the original sequential algorithm from Bill Pugh. Yeah.
So I'm just kind of curious. I think you touched a bit on this in the dual slide and also the combining slide, but kind of more generally, when choosing between like flavors of a data structure, like blocking or non-blocking versions and kind of flavors of those, what are some important considerations with regards to other kind of performance relevant things like cache friendliness, or maybe like some less obvious sort of aspects of that?
This is sort of the subject of Trevor Brown's talk, right? There are lots of practical considerations that impact the performance of a data structure. So a lot depends on the expected workload. So how much contention do you expect to have? If you expect very little contention, you may just get by with a single lock on your whole data structure, right? If you have lots of concurrent operations, you need to look at how many of them are updates versus just lookups. You need to think about how many of them are aggregate operations that are looking at many elements versus local operations that are working on only one element. So you need to understand the workload. Then you need to understand things like how scheduling works on your machine. Is preemption a concern? Maybe you're working in a scientific programming domain for supercomputers where every thread gets its own core and there is no scheduling going on underneath. So you never have to worry about preemption, in which case, non-blocking may not help you all that much. So you need to understand what the system is doing in scheduling. You need to know whether there are asynchronous events that are going to get serviced on your same core. You need to understand the memory hierarchy so that you know how much a cache miss is going to cost you and how likely it is to be satisfied from a nearby cache versus a cache across the interconnect between chips. There's a lot of very interesting work still being done on NUMA-aware algorithms that pay attention to what's located on next to which chip of your machine. The list is disturbingly long.
I want to generalize first question. As probably everybody here knows, for log-based concurrent programming, we can use tools such as Working to verify that everything is going good. And for non-blocking programming, is there any tool or maybe a mathematical notation that can verify that everything is nice?
So basically you're asking what sort of tools exist to debug and perhaps benchmark non-blocking algorithms. There are both sort of practical tools and formal tools. So in the formal camp, there's things like TLA, which may allow you to prove properties of your algorithms that you can state in mathematical logic. There are also model checkers, which will more or less exhaustively explore the multi-threaded state space. And some of those are surprisingly fast, much faster than you would expect, that do sort of a directed search through the space. And even if they don't come back and say, yes, I've proved this correct, if there are bugs, they are likely to find the bug soon. So I recommend the logic approach for somebody who's capable of working with the tools and wants to have really high confidence in what goes in their library. I recommend the model checking for anybody who hasn't been able to make the logic-based approach work for them. And frankly, you can get an awful lot of mileage out of just beating on a data structure and looking to see if invariants break. So you fill your code with assertions and have a lot of threads pile onto it, and it very often will break soon if there's a problem. That obviously doesn't tell you about the absence of bugs, just their presence. But to be perfectly honest, that's the main way I debug things.
Thank you.
Yeah. Shall I go on to the last few slides? Or okay.
What do you think about performance or cost of atomic operations? Are they comparable to each other or to common load and store operation? And from what parameters their performance depends?
I had trouble understanding. I'm sorry.
Performance of atomics operations.
Do you mean atomic operations on a data structure like insert or remove, or do you mean atomic instructions in the instruction set?
Yes, instructions.
The instructions. That's actually something I probably should have said something about earlier on in the talk today. For many years, there was sort of a general folklore in the community that said read, modify, write instructions like compare and swap are slow, and you should try to use them as little as possible. And that was true on early generations of machines. So there were successive Intel machines, for instance, where compare and swap was implemented by locking down the memory bus so that no concurrent memory operations could occur while you did the read, modify, and write. And so the duration of that was the amount of time it took to get all the way to memory twice. And they were really slow, and you didn't want to do very many of them. That's not the case anymore. Modern machines are built by companies that understand that the read, modify, write instructions need to be fast. And they operate in cache and take only slightly more time than a load or a store. What's expensive on modern machines is two things. And Trevor, I'm sure, will be talking about this. One is cache misses, particularly cache misses that go cross-chip, because those can take a couple hundred cycles. And the second is fences that force ordering in the memory order. And most atomic operations like CAS are fences. And their cost comes not from the cost of read, modify, write being atomic, but from the cost of making sure that it happens after all previously executed instructions and before any subsequent instructions. That's going to be, in the 20 or 30 cycle range probably on most machines these days. So the fencing is still somewhat expensive, but we're still talking, the cost of a trivial subroutine call to perform a read, modify, write instruction. So they're not nearly as expensive as they once were. Does that sort of get to what you were looking for?
Okay, yeah. Thank you.
Okay. I have like 2 minutes left, so I would like to give you the titles at least of my last couple of slides.
I think you can take 10 minutes.
Okay.
Slightly postpone.
Okay. So I just had a couple of other things that I wanted to give you hints of because I think they're cool, and if you think they're cool, you should go off and look for papers. One of them is the notion of combining, which shows up in a lot of non-blocking data structures and actually in blocking data structures as well. So it's an orthogonal concept, but it shows up in some non-blocking structures in kind of cool ways. In general, the notion of combining is that sometimes, given the semantics of the data structure that you're building, there are operations that can be combined into a composite operation more cheaply than they can be applied individually to the data structure. And the classic example of this is a stack. If I think about the sequence of pushes and pops that happen on a stack, and in that sequence, I look at an adjacent push and pop, a push-pop pair that happens in that order, where the pop gets the value that was pushed. Because the stack is last in, first out, that pair could go anywhere in the sequence. It doesn't matter that it was right here. It could have been over here or over here in the sequence. So if I could somehow arrange for the pusher and the popper to find each other without bothering anybody else, they could both be happy and satisfy each other and go home and not cause contention with anybody else. So that's the most simple classic example of combining. And the easy way to do it in a non-blocking algorithm for a stack is take something like the Treber stack, but augment it with an array. Call it a combining arena. It's got K slots in it. And when I come along to do a push, say, I roll a die and get myself a number between 1 and K, and I look in that slot in the array. And if it has a pop in it, when I'm trying to do a push, I say, hey, great. I grab the pop, and I give it my value, and I return. If, on the other hand, the slot has a push in it, I try again, look for another slot. Or if it's empty, I sit in it and wait a little while, hoping that a pop will find me. And after a little while, if a pop doesn't find me, then I go ahead and do my push on the tree or stack. But I wait just a little while in the hopes of bumping into an operation that I can combine with. And every one of these slots in the array is in a different cache line, so they don't interfere with each other. And you get lots of pushes and pops under high contention, finding each other without bothering the rest of the array. And you can get remarkable throughput on a stack, which intuitively we think of as an inherently serial data structure. Turns out you can do combining on a variety of other structures. You can make it work for queues, surprisingly, even though they're FIFO, if you're willing to wait a while and mostly benefit when the number of elements in the queue is fairly small. Recently, well, almost a decade ago now, Danny Hendler's group came up with this notion of flat combining, which is a lovely way to exploit the trade-off between locality and combining. So we had a question a minute ago about what makes concurrent algorithms fast or slow, and how do you know which one's going to be fast or slow? And two of the things that impact performance a lot are locality, in other words, how many cache misses do you have, and concurrency. How many things can you get working simultaneously and independent of each other? And sometimes there's a trade-off between them. Flat combining exploits that trade-off and tries to find a sweet spot. Basically, it says, under high contention, if my data structure is sitting in cache, or maybe the top few levels of the tree that is my data structure are sitting in cache on one node of my machine, it might be a really good idea to do all the operations on that node for a little while and make use of the cache locality. And under low contention, it might be better to just let everybody do their own individual operation when they want to. So the idea with flat combining is that threads kind of take turns being the owner of the data structure. We have the regular data structure. The flat combining is an add-on to it that has a combining arena, which is a place to write down the operation that you would like to perform. And when you come up to the data structure, you sort of look initially to say, is contention high? If contention is not high, I just do my operation, and that probably involves some cache misses. If contention is high, then I write down what I want to do. And somebody else owns the data structure at the moment. And while they are the owner, they keep looking through the combining arena, looking for things that can combine with each other, and just doing all of the other ones. So somebody's responsible for doing all the operations on the data structure that come along for a little while. And after a while, it gets tired, and it says, I'm not the owner anymore. The next thread who comes along should become the owner, and they can do all of the operations for a while. And this gives you much better locality than you get with every operation proceeding on its own, and under high contention, it will give you much better performance than you get in kind of the naive way. Last two slides, a lot of work in my group, as suggested in my rambling answer to a question a few minutes ago, has been looking at persistence in the sense of surviving crashes using non-volatile memory. And here you can think of threads that come along and try to make sense of what's left in memory after a crash as running concurrently with, in other words, able to see the state at an arbitrary time in the execution of all the other threads. The problem, of course, is that consistency and our view of memory that looks, if not sequentially consistent, at least reasonable, is built on top of caches. And caches, at least in the near term, are volatile. So when you have a power failure, you lose everything that's in the cache. And what you have in memory is what the cache felt like writing back before the power failure. And that may not be the oldest stuff. It could be some really new stuff. So somebody might have inserted something in a list where the node in the list is lost in the cache, but the pointer to it actually got written back to memory. And I can't use that after a crash. I got a pointer that goes nowhere. So there's a lot of design work that has to be done to make concurrent data structures usable in the wake of a crash, and it involves forcing the cache to write certain things back out in order. And there's a lot of interesting challenges around how to do that efficiently, to try to get good performance during normal operation and still be able to recover in the wake of a crash. And I'd be glad to talk to anybody more about that offline. My last slide is about the other project that my group is working on at the moment that I'm really excited about, and that has to do with user-level management of extremely fast devices, one of which is shared memory. Think of shared memory as a device. But there's a lot of devices these days, like network interfaces or high-end SSDs or GPUs or other on-chip accelerators that are so fast they can perform several million operations per second. One core can't keep them busy, nor can one core afford the overhead of a system call into the operating system every time they want to interact with the device. And as a result, every major data center in the world right now is using kernel bypass services to fast devices, where your application has direct access to the hardware without going through the operating system. And you can make that safe by giving every application a separate page with which to access the device so they can't bother each other. But the operating system is no longer able to enforce fairness. It can't say you're only supposed to get 1/3 of the bandwidth of the GPU according to the contract that I cut with you when I started running your cloud service, right? And if I have two applications that make different size requests, one of them has big GPU requests and one of them has little GPU requests, and the device just alternates between them, the one with big requests is going to get an unfair fraction of the service. So it would be nice if we could get these separate channels of the device to actually talk to each other and let the operating system do its historic job. That's what our project is about, and it works on shared memory too. So imagine that I have an application that historically might have used memcached. Anybody used memcached? Okay, commonly used key value store that maintains information in memory, very frequently used as a cache of a database in an e-commerce application. Memcached provides a service that's accessed over Unix domain sockets. So if my application talks to the server over a socket, says, please insert this key and value pair, please look up the value that goes with this key. But it's in memory, right? So why not just put it in shared memory? Well, because if you put the key value store in shared memory and it represents a cache of the database, and my application and your application are running on the same machine, and mine was written by me and yours was written by you, and you don't trust mine, and that's good because mine has a memory bug in it. If we map memcached into my address space, then my memory bug may walk all over it and destroy it, and that would be bad. And the idea in this project that we're working on that's named Hodor for Game of Thrones fans is to have a library that has more rights than the application does, but acquires those rights more cheaply than an operating system syscall does. So if you trust the library, because it was written by the people who wrote memcached, in fact, it is memcached, you can map it into multiple applications, and the shared space in the middle there is the actual hash table. And now I can perform lookups, inserts, and removes in this hash table using trusted code, but my own thread. I don't have to use the scheduler. I don't have to go into the operating system. I can very quickly perform my operations. And it turns out that you can do this safely, and you can actually do it pretty cheaply on current x86 hardware using a technique that's being presented this very week at the Usenix ATC conference by my student, Mohammed Hedayati. And I'd be happy to talk about that more offline. And that was my last slide. Lists of papers and other stuff can be found online at those URLs. Thank you all for your attention.